In this video, we will introduce the mean value theorem for derivatives and investigate a few related problems. So let's start by just stating the mean value theorem. It tells us that if f is a function which is continuous on some closed interval from a to b and differentiable on the open interval from a to b. So these we would think of as being the hypotheses of the mean value theorem. If these hypotheses are satisfied, then the conclusion is that there is at least one number c in the interval from a to b, with the derivative at c being f of b minus f of a over b minus a. And let me just note the geometric interpretation here. So corresponding to a, we have the point on our graph, a comma f of a. Corresponding to b, we have the point on our graph, b comma f of b. And if we look at the expression f of b minus f of a, the rise, over b minus a, the run, that would be the slope of the secant line connecting those 2 points. So this quantity that we have here is the slope of the secant line connecting points a f of a and b f of b. And looking at our graph, we see very nicely here at least one value where f prime of c is going to be the same. So remember, f prime of c would be the slope of the tangent line, and for these two lines to have the same slope, they would have to be parallel. So there's one point here where the tangent line is parallel to the secant line. And we're guaranteed at least one, but note in this case there's certainly a second value as well. It looks like maybe right about here, if we draw the tangent line, it would also be parallel. So we're guaranteed at least one, but there could certainly be more than one as well. So let's investigate this just from a purely analytic perspective, and let me remind you of the hypotheses. You can apply the mean value theorem when the function is continuous on a closed interval, differentiable on the open. So let's verify that for the function given here, the hypotheses are satisfied on the interval from 1 to 4, and let's find all numbers c that satisfy the conclusion. So let's see here, our function f of x equals 2 square root x is continuous and differentiable everywhere that it is defined. So this would be continuous and differentiable on the interval from 0 to infinity. And since it's perfectly continuous and differentiable there, it is also on the interval from 1 to 4. So what this tells us is that it's continuous on that closed interval from 1 to 4 and differentiable on the open interval from 1 to 4. So let's put a check. The hypotheses of the mean value theorem are satisfied. So now, can we find a value of c satisfying the conclusion? So let me remind you what the conclusion would be. There is some value of c with c in between 1 and 4, where f prime of c is f of 4 minus f of 1 over 4 minus 1. So f prime of c is going to be equal to 2 square roots of 4 minus 2 square roots of 1 all over 3, which is equal to 2/3. So we need to find all values of c that will satisfy this equation. So let's find the derivative. F prime of x is going to be 2 times the derivative of square root x, which is 1 over 2 square roots of x. So 1 over root x. So f prime of c then would be 1 over root c. So 1 over square root c. And what we need to do is find all values that satisfy this equation. So we need to, at this point, solve for c. So we can multiply both sides by 3/2 and multiply both sides by the square root of c. And then to get c out of the square root, we will square. So 9/4 is equal to c. So we verified that the hypotheses of the mean value theorem are satisfied, and there is one such c value where we get the desired conclusion, and that's c equals 9/4. Another similar example, for the function given here, this cubic, we'll verify that the mean value theorem hypotheses are satisfied on the interval from -1 to 2, and then find the number c that satisfy the conclusion. So once again, the function that we're dealing with here, is rather nice. It's a polynomial function, and polynomial functions are continuous and differentiable everywhere. So this is continuous and differentiable on the entire real line, minus infinity to infinity. And what that tells us is that certainly these restricted conditions are satisfied. It will be continuous on the closed interval from -1 to 2, and differentiable on the open interval from -1 to 2. So check, the hypotheses of the mean value theorem are satisfied. Now we need to determine if there are any values c, or determine the value c, that satisfy the conclusion. So there's at least one. Will there be more? So recall the conclusion is that there is some c value with c in that interval from -1 to 2, with f prime of c equaling f of 2 minus f of -1 over 2 minus a -1. So f of 2 is 3, f of -1 is 0, 2 minus a -1 is a 3. So we need to know where is f prime equal to 1. So let's find f prime x. So just differentiating term by term with the power rule, 3x squared minus 2x minus 1. So we need f prime of c, which would be 3c squared minus 2c minus 1 to equal to 1. So once again, we need to solve for c. So how about we subtract 1 from both sides? So 3c squared minus 2c minus 2 equals 0. And we have a quadratic equation. It doesn't appear to factor nicely, so we should use our quadratic formula. So c is equal to minus a minus 2 plus or minus the square root of 2 squared minus 4 times 3 times minus 2, all divided by 6. And this is going to simplify it a bit. This is going to be 2 plus or minus, and underneath that square root, we're going to have 4 plus, so minus a minus makes it a plus. 6 times 4 is 24. So plus or minus the square root of 28 over 6. And these values are approximately equal to, if we use a calculator, minus 0.55, which is in our interval, and 1.22. So there are two values of c, in this case at work, and they are given by the following expression.